Welcome everybody. I'd love to introduce Karianne Bergen from Brown University, who's been working at the connection of explainable AI, machine learning, and geosciences. Welcome, Karianne.
Hi. All right. So hi everyone, and thanks to the organizers for inviting me to speak with you today. Unfortunately, with my setup, I can't see all of you who are on the call. So, but feel free to chime in with questions, or if you put a question in the chat, someone can pass that along to me. So my name is Karianne Bergen. I'm an assistant professor of data science and earth, environmental, and planetary sciences at Brown. I also have courtesy appointment in computer science, and I'm a faculty affiliate in environment and society. And before I sort of jump into my talk, I want to tell you a little bit about my research group at Brown. So I have a good group of students and postdocs working with me, and our work is focused on creating and applying novel machine learning solutions to help scientists to better understand their data, solve complex data modeling and prediction challenges, mostly in the physical sciences with a focus on earth science applications. Some of the themes to our recent research include explainable AI, physics-informed learning, and uncertainty quantification. Some of the types of applications we've been looking at for these tools are pattern recognition, statistical downscaling, and building surrogate models and emulators. And within the earth sciences, we're applying these to different scientific domains. I'll talk in the beginning of the talk about sensor networks and natural hazards. Toward the end of the talk, I'll talk more about the cryospheric science, so ice sheet models, Antarctic sea ice. And then we have some other projects as well. For instance, also have a project related to looking at more local coastal resilience in the New England region. So we have a range of different projects that we're doing in the group. All right, so the outline for the talk today is I'm going to kind of talk about three different projects. I'll talk about my past research, which was focused more on geophysics and solid earth. And this is where I sort of got introduced to the interesting challenges that come up applying machine learning in the geosciences and how I sort of got into this area. Then I'll talk about a recently funded project that's kicking off related to explainable AI for scientific data. And right now we're focusing on instance-based explanations. And then at the end of the talk, I'll talk about some collaborative projects in machine learning and cryospheric science. Cryosphere is the icy part of the Earth, so that's where some of our more recent applications are. So during my PhD, which was in data and computational sciences, I worked on a large collaborative project with computer scientists and geophysicists, and we were working to develop methods for analyzing large seismic data sets. So in particular, we were looking at data sets where we had seismic sensors. These are sensors that measure the vibrations of the Earth. And these sensors have been collecting data for years, sometimes over a decade. And we wanted to go back, reanalyze this data, and try to find the signals from really tiny earthquakes that previous algorithms had missed. So we wanted to find as many of these small earthquakes as possible in these very large data sets. And so as someone coming in with a background in applied mathematics, data, and computational sciences, I was sort of drawn to this problem because it had a lot of interesting challenges. So the data sets that we were looking at are seismic data, which looks sort of like this. This is one day of data recorded at a specific station. Each of the rows in this chart are 30 minutes of data. And so we have each of the rows stacked one on the other. They're sort of overlapping. So we can see one day of data, and this is the shaking in the vertical direction. This took place during a foreshock sequence. So there's a number of sort of large events that we can see. These events have a specific signature. There are different waves that arrive when there's an earthquake. So there's typically an initial arrival called a P wave, followed by a larger wave arrival called an S wave. So this is kind of the signatures that we would see in the data. These larger events are pretty easy to detect out, to pick out with standard algorithms, but there are a lot of really small earthquakes that take place, and these are harder to pick out. And as you go to smaller and smaller earthquakes, they happen more frequently. So very large earthquakes are infrequent. The teeny tiny earthquakes that are difficult to pick out of the noise, those happen much more frequently. And so this data is really challenging to work with. Because we're interested in really small events. One of the challenges is these are very low signal to noise. Also, the background signal is very heterogeneous. So these sensors are ground motion sensors. They're not specifically earthquake sensors. So they pick up anything that's causing vibrations. So that could be like traffic driving by. It could be caused by other natural forces like winds. So there's a range of different noise sources, and the data is quite messy. During foreshock or aftershock sequences like these, you can also get really complex event sequences where there's a lot of signals in the data in a short period of time. And then some of the other challenges are just working with practical data sets. We have data quality issues. There can be missing data. And one of the big challenges that we see generally in geosciences is that although we have really large data sets, we have relatively limited labels. Our catalogs that we have of earthquakes, which could serve as training data, for instance, in a machine learning algorithm, are often limited or incomplete. And they reflect our current knowledge and not necessarily the things that we want to discover. We also generally don't have ground truth. We don't know what the right answer is, which also makes it a challenge to evaluate the performance. So because of all these challenges, I kind of got sucked into this project, and it was a lot of fun. So looking at,
as you're defining what an earthquake is, how do you definitionally differentiate a large truck from an official earthquake? Is it like a depth kind of thing or something else?
So generally an earthquake, an earthquake by definition when you have like a slip along a fault. So that's what it is from kind of a scientific standpoint. As we're thinking about the events, generally what we're looking for is an event that we're going to see at multiple seismic instruments. So it's going to be something that's produces a signal over a sort of a larger region as opposed to something like a truck driving by, which would just create local vibrations. And ultimately, if we can then use the information that we extract to sort of locate the event and characterize it, then you would be able to sort of determine that it was an earthquake. But it is challenging. For instance, earthquakes and explosions look similar and may be seen over a large area. And so there's other ways of distinguishing what kind of signal, but the sort of main one is whether it can be ultimately located.
Got it. Thank you.
All right. So one of the sort of, at that time when we were working on this project, which I started working on about 10 years ago, the most widely used technique for detecting these really tiny earthquakes was called template matching. This is basically doing waveform pattern matching with known events. So you might have a series of events. These are recorded over a series of years. If we observe this first event, we could take that event waveform, we could sort of scan through our continuous data and look for other events that had high similarity to it. And so if we applied this to sort of years of data, we may be able to pick out these other signals that look nearly identical. And we measure that using the normalized cross correlation. So this is a commonly used approach to pick out these small earthquake signals. If you apply this to multiple stations, again, in your network, it can actually be a very sensitive detector. But the disadvantage of this approach, despite being very powerful for finding these small events, is that you basically have to know exactly what your signal looks like. It doesn't generalize to new events. And oftentimes the catalogs that were available were very limited. You might only have a record of a few events in a particular area or part of a particular sequence. And so you were very limited in what you could find. Basically, you're limited by what you already knew. And so we were interested in, can we detect these sort of repeating events, which we know that many of the earthquakes we observe have these sort of repeating signals. Can we do that without having to have prior knowledge of what the event looks like? And can we use this to discover new template waveforms that we can then use for detection? So that sort of motivated our approach that we developed. So we wanted to have a sort of a data-driven approach to detect these. We developed an algorithm we called FAST, which is a scalable detector for small events. This is an unsupervised detector. We're assuming that we don't necessarily have really high-quality data available. So we wanted something that we would be able to use in sort of any scenario, even if we had limited data. And so we tried to design it in a way that was kind of oriented towards discovering new repeating signals and not relying on, whatever the limitations of our existing catalog were. And so we wanted to build a model that would be more generalized and be able to discover new signals. This method was also really reliant on domain knowledge. We had this idea of the similarity search built in, that earthquake waveforms are similar to other waveforms that have been observed. And so that's built into the structure of the detector. I'm not going to go into this particular method in too much detail. I just want to kind of give you a flavor of the problem so I can focus on some of the more recent work. But we had our method for unsupervised detection. So we would apply this initially at each seismic instrument separately. So the data that we would have would be these time series of waveform data. Again, these might last for up to years or decades of data. We would take our time series and we'd break it up into little short time segments. These are short waveforms, and we would extract a set of features from those. Here I have kind of a set of features visualized. We call those waveform fingerprints. And then we used an efficient similarity search algorithm. The one we used was based on locality-sensitive hashing, which is basically sort of clustering together earthquakes that are more likely to be similar to each other, so we can quickly retrieve the most similar pairs of earthquakes from the data set. We do this sort of efficient similarity search, and we get this sort of output that tells us what are some potential candidate earthquakes by identifying these segments of our data that are similar to each other, and those similar waveforms serve as our new sort of candidates. Using this sort of approach, we were able to get a substantial speed up over using sort of a brute force search for these repeating waveforms. If we were to do sort of a slow, exact search, not using clever algorithms, we could only really process at most a week of data. We previously processed 7 days of data and took over 200 hours to run. Using our fast algorithm, we were able to scale up to 10 years of data, and we could run it overnight. And we also made our code available to the sort of seismology community to use. And so this was, sorry.
Is this clustering of a bunch of unlabeled data, so like a regular clustering kind of algorithm, or is it against a known database of fingerprints?
It's yeah, we don't have a known database of events. So we're just searching. The way that we're identifying the candidate earthquakes is just based on their similarity to other events, and then sort of the temporal structure. So you would expect to see, because we have these sort of time windows, we would expect to see those kind of lining up in a certain way if we were seeing earthquakes, as opposed to, that was one way to eliminate false detections. So we're just searching sort of blindly for repeating signals. And then we had some ways to eliminate false detections, including the sort of temporal structure, and also using multiple stations in the network, which was kind of a big part of what I was working on with the project, was how to extend this to multiple instruments.
And Shane, you have a question?
Yes. So when you do similarity search and clustering, I'm guessing maybe like a car signal could be clustered with other car signals, which might be a different cluster from an earthquake cluster. Is that so? You could get different varieties of signal, not just earthquakes.
Yeah, so we had a series of ways to separate out the earthquake signals from other kinds of repeating signals. So some were sort of these filters that we had. For instance, if we had a signal that was just constantly repeating all the time, then we were like, okay, this is probably like a data quality issue. Maybe there's something near the sensor that's like setting it off. And so we would sort of remember what those signals look like and ignore them. So we had some sort of flags like that. And then we also used data from multiple seismic instruments to make sure that we're seeing the same kind of repeating patterns at multiple stations. And so that was actually the kind of main focus of my thesis project, was extending this approach to multiple instruments. And that's a good way to get rid of false detections. We also looked at using sort of machine learning to try to filter it out, but actually using the physics works better. So the physics is kind of looking for sort of coherent patterns across the network, that we would have something that was consistent with wave propagation to multiple locations. And so we were specifically searching for patterns that aligned with what we might expect to see if we were seeing signals coming from earthquakes that were propagating in space and time.
Pedro?
All right.
Oh, yeah. Sorry. Quick question on the previous slide too. Can you talk a little bit about the feature extraction part? Like what are some features you used, and which ones end up being most important, for example?
Yeah, so we used we converted the data into a time frequency representation. So we used a spectrogram, and then we extracted features based on sort of like wavelets that were normalized, so that we would actually sort of prioritize signals that were less frequent in the data. We did some sort of standardization. So I'm happy to send. I have a whole paper about how we did that, if anyone is interested. But we're using the spectral representation of the data, so the time frequency. So they actually look like we convert them into sort of images, and then we take image patches and extract features from those using wavelets.
All right, thank you.
Thanks.
Yeah. We tried to learn the features, but because earthquakes are relatively infrequent compared to the background signal, you actually have to, if you want to learn the features, you have to do it in sort of a supervised way to give more weight to the actual earthquake signals. So in the end, we use this sort of engineered features that were based on approaches used for audio data, and it worked pretty well. So we stuck with that. So in terms of kind of the performance that we got, this was a method that was much higher sensitivity than standard catalogs. We would typically get 1 to 2 orders of magnitude more events. For example, in one study that my colleague used where she applied this to a sequence of induced earthquakes. She found 174 times as many as in the original catalog. We saw that it's more computationally efficient. We can process 500 times as much data, so going from a week to 10 years with a reduced runtime. So we're able to scale it up, which is necessary if you want to find these repeating signals, which often can occur sort of there's a long time gap between them in some cases. And then by extending this to multiple sensors, using the sort of full seismic network, we can really reduce the false detections, along with some of these other approaches, some kind of common sense like filtering that we apply to the algorithm as well. We can get relatively few false detections. And so that was a project that I was kind of the main focus of my PhD research. But as someone coming kind of into this project from a data science background and kind of being introduced to geosciences, there were some interesting takeaways for me from the project that kind of got me interested in staying in this space of research. And so one was the challenge of using these data-driven algorithms to try to discover new things in scientific data, really being focused on kind of discovery. One of the challenges that we had is that the data sets that we have a lot of limitations. And one of those is that they reflect our current knowledge. Like if we have catalogs we could use to help us learn from, those reflect what we're currently able to detect, what we currently know about our data. And so you have to be really thoughtful about how do we want to design our systems, our new analysis pipelines in order to discover new things and not be limited by what we already know. Another thing I found is that a lot of the sort of methods and the assumptions that they're based on in some of the standard machine learning literature doesn't necessarily reflect what real tasks and data look like. So they often, look really nice on these kind of curated benchmark data sets, but when you try to apply them to real data, it's a completely different story. But the advantage there is that as someone interested in data science, that means there's a lot of opportunities for innovation, for new methods to kind of tackle some of these challenges, and also to have impact by collaborating closely with scientists on these kinds of problems. Another big takeaway was that the scientific knowledge and physical models were really important in this particular problem. You sort of have this bias of always wanting to jump to like, okay, let's do everything in a data-driven way. Can we learn, the features? Can we learn how to throw out false positives? And in the end, a lot of times it was taking into account sort of the domain knowledge, some of the physics of the problem that actually would get us a lot farther. So one of the best ways to eliminate those false detections was to look at multiple stations and make sure the patterns we were seeing across the seismic network were consistent physically with what you expect for an earthquake. And so we sort of built that into our sort of pattern mining approach and only looked for patterns that sort of met certain criteria that were based on the physics. And it was also really interesting kind of to be part of this interdisciplinary collaboration where everyone's kind of speaking a different language. And so I think having this interdisciplinary training, people on both sides, the geoscientists where, I was teaching them some of the data science, they were teaching me some of the geophysics, and being part of this collaboration was really important so that we all had kind of the same language and were able to really discuss and make good progress on this, problem in a way that, in each individual sort of contributor wouldn't necessarily be able to do. So after working on this project, I kind of had some thoughts about, okay, well, how could, machine learning better be applied in geosciences? How could we use it to advance this field? And so I got together with some of my colleagues in this field. And in order to kind of put our recommendations out there, we did it through writing a review paper where we had this kind of section of forward-looking section of recommendations, in particular focusing on challenges and opportunities in using machine learning in the geosciences. And this paper came out about 5 years ago. And at that time, there were some of the challenges are the same and some have sort of were a little bit different. So one of them at the time was that there really weren't a lot of these kind of high quality, large labeled data sets, either for training supervised models or even for evaluating models or comparing how different algorithms were doing. It was very frustrating because every person doing research in this area was kind of setting up their own data set, creating their own benchmarks, their own way of scoring themselves, and you couldn't have any sense of like which of these algorithms are actually doing better. People also weren't sharing their research code, so it made it hard to run other people's algorithms on your data. And so this was a big limitation, sort of holding back innovation in this field. There were also some kind of research culture things that were challenging. There was, I think it wasn't as common as it is now for people to have the sort of data science skills among the sort of geoscience community. And there also weren't as much kind of focus on some of these applied machine learning problems. It was really hard to find, for instance, venues to share this kind of research, places to publish it, funding opportunities. And so that was a little bit challenging. as well as the sort of, there's different, the data sets themselves, the challenges, often have sort of slightly different needs in the geoscience sort of space than a lot of the algorithms that are being developed in the tech community, which are often more geared towards like human generated data or certain types of data. And so there was this kind of research component to it as well. And so we made this kind of, this is a figure that sort of we put in the paper that sort of summarized that, kind of needing improvements among geoscientists and open science, needing more benchmark data sets, data sharing, more sort of education collaboration. And then my interest was kind of over here in like the different research areas that would be particularly relevant. And so that was sort of 5 years ago. Things have advanced quite a bit in this field. About 5 years ago is when it really, I would say, started picking up using these kind of machine learning techniques and other data-driven techniques. And so more recently, I was part of a group that wrote a review paper that was about scientific discovery and AI, scientific discovery more generally in AI, but many of the things that we highlighted there also apply in geosciences. So just put this here as a reference. But within the geosciences, there's machine learning is being used much more broadly than it was. When we wrote this review paper, almost all of the examples that we could find of machine learning being used in geosciences was to help basically do automated data processing, just to kind of do routine tasks, sort of pattern recognition. And it's really expanded a lot since then. So machine learning is now used for things like not just data analysis, but data collection, curation, and refinement. There's more of a focus on things like learning meaningful representations of scientific data, especially building these like larger models that can be used together with, say, transfer learning and applied to a range of different different regions, different problems. And then using it for things like generating scientific hypotheses. And also a big one, at least that we've been focusing on my group, is machine learning driven experimentation and simulation. So kind of moving away from just the pure data processing and doing approaches that involve also modeling as well, and sort of combining machine learning with the physical simulations and models. There's also expanded toolboxes. So at the time, it was very simple in terms of the machine learning approaches people are using, but although many of these tools have been around since earlier than kind of the time when our paper came out, there's been a lot more adoption of kind of more advanced techniques. And some of that comes along with a greater kind of interest in education in that field in data science. But one of the sort of areas that I think has been really exciting in terms of the cultural shift in geosciences is that now there's a lot more embrace of this sort of open science culture and sharing data sets. So now there are, for certain kinds of problems in geosciences, there are kind of machine learning ready benchmark data sets that are out there. So for instance, for this problem of detecting earthquakes, if you're looking at sort of conventional earthquakes, there are now very large labeled data sets that you can use to train models. So that field has really moved a lot more towards using these large trained models and then maybe using transfer learning to adapt them for specific tasks. So for instance, the Stanford earthquake data set has over 1 million labeled waveforms. There's also a number of different groups that have put out like regional data sets. For instance, here's an example, one from Italy, and starting to share their code. So it's become much more common for researchers in this field to make their code available, make them often easy to use packages. And so that's really advanced research in this area pretty substantially, which has been exciting. It's also in terms of like this kind of culture around publishing conferences. There's a lot more sort of interdisciplinary work in this space now. A lot of machine learning conferences will have workshops related to earth sciences or climate change. There's also in the earth science conferences, it's really common for there to be now machine learning sessions related to pretty much any topic. And there's actually a growing number of interdisciplinary journals at this intersection. So journals like Environmental Data Science, which is part of the Cambridge University Press. The American Meteorological Society has a sort of AI focused journal. And the American Geophysical Union, which is the largest professional society in geosciences, just started its own kind of machine learning and computation focused journal, so that these methods that kind of cut across different geoscientific disciplines can be sort of published together. So previously they would have to be in sort of a field specific journal like geophysics or cryospheric science, and rather than kind of one journal that where people from all of these different subfields can see them. There's still a lot of work to do in this area, though. That's kind of what motivates some of the work that my group is doing. So even though we have these large benchmark data sets, there's still issues with data quality, and limited data sets is still a major challenge for geoscientists. For some of these big foundational problems like earthquake detection, that's a super important problem. in earthquake science. And so that's something that the community has put together, these very large labeled data sets. But for other problems where you're more data limited, where it's harder to kind of build up those kind of community level data sets, the data sets are still often small, and the quality of the data may be poor. There also isn't a lot of theoretical guidance for scientists who want to use these tools. So things like how well is their model going to generalize out of distribution. This is particularly challenging in climate applications where it's hard to say how these models are going to generalize to say future climate scenarios, and the degree to which you should use kind of domain knowledge, rely on that versus using data-driven approaches. And also another big one that I hear is around transfer learning, like what's the best way to kind of use transfer learning, and how much data do you need to build a good model? Should you retrain your model from scratch? These are things that scientists still kind of struggle with in applying these methods, and I hear a lot about from them. There's also need for more tools for multimodal and multi-source data. A lot of times scientists are looking at data. They have all sorts of different instruments, ways of getting data. And a lot of the research around kind of multimodal learning is usually focused on things like text and images, or video and text, things like that, rather than like a whole array of different, say, sensors that are maybe measuring at different scales, different resolutions, different sampling rates, and things like that. And then there's a need for sort of the machine learning to be trustworthy. A lot of scientists are really skeptical of machine learning. They see it as this kind of like black magic. They're like, I don't know what it's doing. I don't know why it's telling me this. And so there's still very much a culture of that in some of these scientific fields. And so they want things like to know how confident their model is, so things like uncertainty quantification. And there's a lot of discussion around black box models. Scientists who want to, one, verify that their models are doing something that makes sense, so using it to sort of verify what models are doing. And also they want to get insights from their data. They want to be able to learn something new. It's great if a black box model is making good predictions, but a lot of times what they really want to know is what are those relationships that allow us to make those predictions. And so that sort of motivates some of the work that my research group is doing. So I'm going to sort of move on to the next section unless there are other questions about this. Okay, not hearing anything, so I'll go on to this new project that I'm looking at related to explainable AI for scientific data. So as I mentioned with this kind of project in earthquake science, two of the main takeaways were that it's, this kind of challenge of discovery in scientific data and the importance of scientific knowledge. And that's something that I see a lot of hesitation around, as I mentioned, for scientists adopting these techniques. So, deep learning is becoming more popular in these fields, but it does have some limitations that are really critical when you're working with scientists. So one is that if you're using fully data-driven models, they may learn solutions that don't make physical sense, or it's kind of learning something that runs contrary to what we know from domain knowledge. So that's always a concern. Again, uncertainty is something that's really important in a lot of these applications, and I'll talk about that later with the cryospheric science project. And then these models are black boxes, and there's just a lot of discussion around that. And so this was an area that I was sort of interested in looking into a little bit more. I played around with a bunch of different kind of explainability techniques before sort of settling on a direction that I found interesting, which is looking at sort of instance-based explanations. And so I'll talk a little bit more about the project that we have going on related to that. So we have a new project that's funded by the Office of Naval Research under a collaboration called the Scientific AI Center. And we're looking at trying to develop new intrinsically interpretable machine learning architectures that are geared for scientific data sets. So things like spatiotemporal data or other data sets that are types of data that are particularly relevant in the sciences. And then I have a postdoc and graduate student who are involved in this. And so the idea with the kind of explanations we're interested in here are instance-based explanations that we're going to use to explain our models. And so the idea is that we want to build a model that we can explain by relating a new test observation to a set of prototypical examples. And those examples sort of live in the same space as the data. So we're sort of comparing our new test observation in some way to existing data points, prototypical examples, and that's how we're going to explain. And these prototypical examples are actually going to be learned in the network, and they're part of the sort of neural network architecture. So they're part of the logic of how the model is making a decision. So it's not that we're coming in after the fact and like finding relevant training examples. We're actually kind of building this into the logic of the model. And I have some references down here to these types of approaches. And so just to kind of play around with this approach, I have an example. This is kind of older work, but it's just to show you some of the early exploration I did of this was these approaches can often start with a model, an architecture that you're already working with. And then you often will start with the model, you can modify the base model and sort of add this extra component that gives it more interpretability. So for instance, one of the models that's being used for detecting earthquake signals is just a simple one-dimensional convolutional neural network, which works surprisingly well. It's sort of competitive with like the more like modern transformer-based architectures. And so for this model, what we can do is we get rid of the sort of final fully connected layer. We look at the convolutional layers as a feature extractor, and we replace the fully connected layers with what's called a prototype layer, and that's where we're going to get improved interpretability. And so this is going to be, we'll have a model that has roughly the same number of parameters, but it's going to use different calculations, and it's going to allow us to kind of make these comparisons to explain our predictions. And so the sort of visualization of this, this is with an image, is you will have your test example, so in this case an image, you'll encode it using those kind of feature extraction layers. Then we'll have our prototypical examples from the data, which also live in this latent space. We compute the distance in the latent space between the prototypes and the representation of our new test point. And we then use those distances as the features that we use to make the decision. So it's just based on those distances. And so this allows us to sort of visualize what the model is doing to make decisions. So this is an example with a waveform. We have a little piece of a P-wave arrival. And we have these sort of prototypes. These are not the greatest prototypes. These, again, it's sort of earlier work. But we can see these like waveforms. These are the vertical channel waveforms. And then for each one, we have sort of a similarity in the latent space. And so we can see which ones were sort of more relevant to making this prediction. So that's kind of the type of output that you might get from an approach like this. And the reason that these kind of instance-based approaches were sort of interest for me over some of the other kinds of techniques that were out there is because of what my experience working with this kind of earthquake detection problem. And it kind of takes me back to this idea of template matching, which is we originally started, we wanted to find these repeating earthquakes. And we had this idea of we had template waveforms you could use to detect other signals. But this approach didn't generalize. So the idea with the prototypes is that we're going to get something similar where with our earthquakes, we could say, I know that this signal is an earthquake because it looks just like this other one that we've seen. And so we have this kind of confident prediction. We kind of know where our prediction came from. And the idea here is that we're going to still have these sort of instances of waveforms, but rather than having to have a fixed set of known templates, we're going to learn some templates that can be used to more generally for detecting earthquakes. So that was kind of one of the reasons why this particular type of instance-based explanation was, I think, of interest to me, and I think in many scientific applications is a useful way of explaining predictions. And so, sorry, sir.
Yeah, question. These learned templates, like, I guess, how do you learn them? How do you know that they're, I guess, insightful? I'm not even sure what that word means for learning.
Yeah, so that was the problem. This is early work, so these are actually not particularly insightful prototypes. What you would typically do is one way to do that, to make sure that they're insightful, is to force them to be data that belongs specifically to the training data. So say, basically constrain them to be examples from the training set. Or a selected subset. You could have a sort of a pool of potential, for instance, potential waveforms that could be your template or your prototypes, which in this case would kind of become your templates. And then the algorithm would select those in the training process.
And then suppose that you have something like this. So then do you have a workflow in mind for scientists to be given that this prediction is based on these templates, not those templates? And what does the scientist do with that?
Yeah, well, I can explain that's the next part. Maybe will answer your question.
Okay, so I'll hold it down for then. And maybe one last thing is, this smells a lot like an attention mechanism because you're attending to some subset of templates. Mm-hmm. Is that to what extent is this just it's a transformer like an LLM?
Well, it's not self-attention.
Yeah,
because
I mean,
the dictionary is fixed and it's external.
That's fair. No, it's a good point.
yeah, and I think part of the idea of this is that a lot of scientists are using much more simple architectures like convolutional neural networks and these kind of things. And so rather than, I mean, there's work on like, okay, can we understand like the, kind of digging into like the, the sort of attention, using that to like interpret. And in this case, it's more of like, can we kind of substitute out some of the layers and give people something that's more interpretable than what they would have otherwise with similar accuracy, kind of by making that kind of final layer have some sort of explanation associated with it.
One more question, Artem.
Yeah, Karianne, I'm wondering, so as you're considering these templates, so are you looking at them as like true templates that are as close as they can be to the, let's say in this case, a target waveform, or are you considering them to be more like basis functions that the target waveform is decomposed into?
It wouldn't be like a basis function, no. You'd be looking for like high similarity to specific instances.
Right, but maybe I'll elaborate. So let's say the actual phenomena is really complex, and so in this case, there are several types of wavelets that maybe have to be combined in, let's say, a linear way in the simpler form to get the waveform. So are you, as you're considering these templates, are you trying to sort of recreate them in sort of the most accurate form as a unit? Or is it okay to have sort of multiple templates, let's say dozens, that have a high match to what you're observing in the field?
Yeah, so there's a whole body of literature on these prototype-based techniques, and some of them, and there's sort of techniques that do both, I would say. And some use sort of positive, and there's some that use positive and negative evidence. There's some that use kind of parts-based components. So there's a lot of different ways that you could use these kind of techniques.
Right, thank you.
Yeah. All right. So the sort of direction that I've been working with a postdoc, and she's kind of played around with this technique a bit and proposed this approach that she's called named PV and J. She's good at coming up with acronyms. And so the idea in this case actually is it's a little bit different way of generating instance-based explanations. And in this case, her idea was rather than having a fixed set of prototypes, to actually have them be sort of sampled from kind of a larger set, like for instance, from the training data, in order to generate kind of multiple different predictions and explanations. So basically getting an ensemble of predictions and an ensemble of explanations. And so this is something that's, again, is kind of work in progress. So we're still working out some of the details, but she's, applied it to some kind of simple benchmark so far. And so in this particular case, what she does is in the inference step, we generate an ensemble of predictions by sort of sampling different prototypes from the training data, sort of separating them out, into different classes. And then this allows us to get a better estimate of the model confidence. Since we have an ensemble of predictions, we get a range, we get multiple predictions, and we can sort of compare those. And then when we have ambiguous cases, we can get an explanation sort of for why. So we can sort of look at the particular instances that were driving the different predictions in those cases. In her experiments, just using kind of, these are very simple experiments using just a small convolutional neural network with just a few layers and using data sets like MNIST and fashion MNIST. It doesn't result in any sort of loss of accuracy. So it's similar to if you were to just use a kind of standard neural network with the fully connected output layers. But what we get is we get sort of these explanations for where the model is sort of disagreeing about or ambiguous in terms of the predictions. So this is an example from fashion MNIST where the ground truth is a coat. It looks like this. The output of the model, it says it's a shirt slightly, but it's sort of unsure. Sometimes it thinks it's a coat, but you have this sort of, it's low model confidence. It has kind of a roughly 45-55 split between the real class and the incorrect class, which it's predicting. But we can sort of visualize the specific instances in the data that resulted in these conflicting predictions. So on this side, when the model thought it was a coat, it was because it said this image looks a lot more like these examples of coats than it does like these shirts. And so that's where we got that prediction. Whereas when it was predicting that it was a shirt, it was saying, well, this particular example, it looks a lot like these particular shirts, and it looks less like these coats. And so that's where we can sort of visualize like why is it making these predictions. And these aren't just examples in the training set that we're finding, like this is in sort of the logic of how the model is making the decision. So it was just, in this case, correctly picking coat because these were similar. And when it got it wrong, it was because these shirts were similar to this coat. Another thing that we find is that using this kind of approach, it gives better sort of confidence estimates for some of these than you would get with a sort of if you had just the standard sort of softmax layer, which usually is overconfident. So in this case of the coat, it was, if you have was kind of the standard fully connected layers, the softmax would say it's like really confident, it's a pullover in this case, whereas with our model, it's a little bit more even, and we can kind of, again, get an explanation for that. And then when it's right, we also can get some information, like this is a correctly classified ankle boot. And here we can see like specific examples that we're driving that prediction. Again, this is ongoing work. So we're also looking at using these distances in sort of out of distribution detection, which is something that's valuable for scientists. They want to know when they shouldn't bother using the model because the data are too far out of distribution. Starting to do some localization, identifying kind of which parts of the image by combining this with class activation maps. And then we're looking at applications to some scientific data sets as well. So that's kind of ongoing work that I'm doing with this postdoc, Hillary. Sorry. So if there are...
Young.
Yeah, I guess we could you could also look at the calibration.
Mm-hmm.
Yeah, calibration metrics like ECE.
Yeah. Yeah, we're doing, so we are still working on it, but some of the things we're looking at are like the, kind of the distribution of the outputs as well, like, and trying to see if it can help us, like if we can take sort of these values that we're getting with the similarities and getting more information out of that. So yeah, looking at the calibration, looking at the outer distribution piece, that's definitely an area that we're trying to look at in the sort of next steps.
Right. I guess implicitly, I guess the point I was trying to make is the work that you're doing seems to have at least two contributions. One in the explainability front,
Mm-hmm.
but it's possible that your work also makes better calibrated models.
Yeah, I don't think we've looked at that specifically yet, but it's something that we want to look at because we think that we're still sort of exploring like, what other advantages could this have for scientists besides just the sort of explainability piece. And so that's where, but I'm not aware of what sort of like what metrics if she's looked at any metrics for that recently or not.
And Pedro?
Yeah. So for the scientific applications piece of
Mhm.
this,
Yeah.
instead of, let's say, just purely learning the templates from data,
Mhm.
if you guys thought or consider something like you come up with some physical knowledge that tells you the template should be this, or like
Mhm.
at least part of the template should be that. So like somebody can say, look, maybe we should use these 5 templates or 10 templates, and then maybe we can learn the rest of the templates or something like that. I'm not sure if that could be useful, but is that something that people think about?
Yeah, so one of the big challenges, and especially when I started working on this, is I was letting the prototypes kind of move around freely and just be whatever. And it was really challenging to set up a loss function so that they would be somewhat meaningful. And so this is something that's, for these methods, there is kind of a lot of challenge around that. And most of the literature just approaches it by projecting the prototypes onto sort of the nearest training data and sort of forcing it to be a training example. But you wouldn't have to use the full data set. You could take you could take a subset of the data that have been carefully selected. I've also talked with my PhD student who's also working on these kind of instance-based explanations as well, about like maybe we could, put in other kinds of kind of things that aren't necessarily actual training examples, but you could say take other like basis vectors, like we could maybe apply like PCA to some of the data and see if, using some of those modes, for instance, would make good templates or trying to kind of other approaches, but we haven't explored that too much yet. Mostly what it was through kind of the initial exploration through trying to tune the loss function in a way that would give you sort of, I would say like visually appealing, but maybe not necessarily like it's hard to say if they're scientifically useful. But yeah, if you can, it's hard to define like what a good explanation is mathematically. So that's kind of one of the problems. But I think using domain knowledge and sort of constraining the set of things that we're considering is definitely an interesting area to explore. But for the most part, people just constrain it to belong to the data.
So one thing that, I mean, this actually is interesting, partially because it's not even a scientific thing. This is a model debugger. But one thing, because this you can be used for many things, but one thing that you can do for science is I often want to know how this relates to theory. How can it modify my understanding? And this brings me to algorithms for bias correction for, let's say, climate models, where I want to say that the climate model is wrong exactly where, or I have 10 climate models, in what scenarios are each one of them right? So it seems like the prototypes may be more generalizable or insightful if they are predictions by different families or parameterizations of theories, right? Say that this example is supported by this theory 20%, I guess like a Bayesian prior in a lot of ways, because arguably your attention weights are Bayesian priors. Maybe you can be doing Bayesian priors onto theories, not examples.
Yeah. There's definitely a lot of, I mean, again, this is a project that it's just starting, it's been less than a year that we've had it sort of going on. So there's a lot more to do. But one of the graduate student who's working on this is really interested in looking at kind of weather and climate patterns with it. And so I think that's a direction that we'll explore more right now. I think her focus right now is looking at kind of how to explain spatiotemporal patterns instead of just, when you just have kind of a fixed image. So.
Yeah, and I can imagine if you go in there, then simulation runs. Then you can have a ton of examples.
Yeah.
Cool. Thank you.
All right. So we're in the last part I want to talk about, and I'll have to go through these a little bit quickly, a couple of examples where I'm working with students. We're working on a little bit more applied projects, and these are both in cryospheric science. So these are sort of the scientific questions we're looking at, and then we're using machine learning to help us address them. So the first is, how much will the Antarctic and Greenland ice sheets contribute to future sea level rise? And the other one is looking at how will the changing climate impact the navigability of the Arctic? And so these are some questions that we're looking at with machine learning. For the first question, how much will the Antarctic and Greenland ice sheet contribute to future sea level rise? This is a problem that scientists would typically tackle by performing targeted experiments using basically large simulation models of ice sheets. So they would have these sort of climate models, we have ice sheet models. These models are very computationally expensive, but that would be the sort of approach they would take to look at this. And so you'd use models to generate these kind of different projections. This is a plot chart from the IPCC that's looking at trying to project mean sea level change out to the year 2100, which is sort of the target we're looking at here, under different sort of future scenarios. And so these are all based on these large kind of simulation models. But these models are very expensive to compute. And so the question that we're interested in is, can we use machine learning to emulate these models, or can we use machine learning to build surrogate models that sort of capture the key kind of patterns and trends that these models are capturing using the more kind of detailed physics, so that we can do more rapid experimentation or sensitivity analysis. And so this is a project that we did in partnership with some leading experts in cryospheric science. So my colleague here at Brown, Baylor Fox Kemper, who is the lead was the lead author of the cryospheric science chapter in one of the recent IPCC assessment reports, and then two leading ice sheet modelers, Helen Struzzi and Sophie Nowicki, who work on the Antarctic and Greenland ice sheets and are leading the sort of research on those modeling. And this work, we actually have our first paper out. We also have a couple of other papers that are in progress related to this project. And so the idea is to build a machine learning based emulator for the models in this kind of larger project called ISMIP6, which stands for the Ice Sheet Model Intercomparison Project. This is an ensemble of different models that are trying to project and understand sea level out to the year 2100. So these are models that the sort of quantity that they were trying to get out of them is that projected sea level change. And we started with the Antarctic ice sheet for our first paper. So we're trying to build an emulator. And for those who aren't familiar with the sort of concept of emulators, these are also often called surrogate models in other disciplines. They have sort of different names. In climate, they like to use the term emulator. So these are smaller scale models that are used to approximate more complex models. So with a climate model, we might have our inputs, which we call forcing agents. And then we have all these other sort of dynamics that have maybe complex models that are very computationally expensive. They might be interconnected, things like the ocean dynamics, atmospheric physics, sea ice, all of these different aspects in order to compute our expected sea level contribution. So these models might take weeks to run on a supercomputer. They're very complicated. But once we've run these models, we have examples of the inputs and outputs of these models. The idea is, can we train a simpler reduced complexity model like an emulator to go directly from the forcing agents to our estimates of sea level contribution? And so that's something that we're trying to do using machine learning in this particular case. And so we did this using in this case, we have a pretty simple architecture. It's an LSTM. To project out, we're using data from Antarctica, and it's aggregated into these different sectors, which is how the data is typically being processed by the people in that field. So we're predicting based on different kind of forcings or different quantities that are averaged over these different regions in Antarctica. Then we compare to the sort of prior state of the art, which was a Gaussian process-based emulator. The Gaussian process-based emulator is pretty simple. It actually only used one variable to force it. And we find that our LSTM-based model is better at predicting the ensemble mean, so matching the sort of average of all of the ensemble of different climate models. It also does a good job of matching each individual model, and it gets the sort of distribution at 2100 much more accurately than the Gaussian process estimator. And we're using the LSTM, we're using Monte Carlo dropout to get some estimates of the uncertainty on that. And then due to the sort of computational advantage of using the LSTM, we can give it more data as inputs. We can give it higher dimensional inputs than the Gaussian process. And that allows us to use a richer set of forcings, and that gives us this better performance. So the better performance is driven mostly by the fact that we can feed the LSTM more data, more inputs. And this is, again, it's an ongoing project. We have this sort of paper I'm happy to send people the reference for. We're extending this to the Greenland ice sheet. We're actually now using as the inputs kind of the original 8-kilometer grid instead of the aggregated data as well for Antarctica. We're looking at quantifying the sources of uncertainty. Uncertainty is really important to climate scientists, and especially these models are being, and the estimates of sea level contribution are being used by the IPCC. And that's the information that's often used by policymakers. So having uncertainty there is really important. And so we have a more data science focused paper that is in kind of the works about the uncertainty associated with these models. And we're also trying to explore other model insights and try to understand. One of the things that we're looking at now is the ability of the models to distinguish between the different climate scenarios and what sort of inputs are necessary in order for us to be able to tell which climate scenario we're looking at. So again, that's an ongoing project, and I'm happy to send the paper that we have, but there should be a few more coming out soon about this particular project. So we have our machine learning based emulators.
So this approach sounds very generic. Like, to what extent is this locked to like climate use case or a sea ice use case, and to what extent is it just can it be applied to any time series simulation?
Yeah, so I mean, the emulator in this case, it's a pretty simple emulator. Like, we're just basically taking the inputs and feeding it into an LSTM. So the idea here is mostly just to like try to replace, I guess the novelty of the initial paper was really the application of kind of machine learning based emulators in this particular domain, as opposed to statistical emulators like a Gaussian process. And one of the reasons people like Gaussian processes is because you can get some sort of uncertainty associated with it. And so we showed that, there's techniques out there to do that with neural networks too. It's not something that you necessarily have to lose if you just by going to neural networks. And so in this case, we use MC dropout because it's easy to explain to climate scientists and kind of matches their notion of ensembles, which is something that they use a lot and they like. And so they like that approach. But now we're looking at other ways of quantifying the uncertainty. And so that method, the student Peter who's working on this, he's been testing it on other data sets as well, other time series. And today we were talking about applying it also to images. So the uncertainty piece is more general, and the sort of emulators are widely used in climate. And we actually have a couple other climate related projects that are using emulators as well.
Cool. Yeah, thank you.
Yeah. All right. And so I'll go quickly over this final project. This is another project that's looking at cryospheric science. So this is a question of how will a changing climate impact the navigability of the Arctic Ocean? And so the idea here is that, when we have sort of melting sea ice or have sort of shorter seasons in which the Arctic Ocean is covered with sea ice, this may open new shipping routes or allow shipping routes to be accessible for larger portions of the year. So this is a little plot. You can see some kind of shipping routes. In this study, we're looking specifically at the northern sea route, which is along the coast of Russia. And one of the challenges here with trying to determine, are these routes going to be open as they pass through these like straits? And the straits can't be resolved in climate models like the CMIP6, which are used again widely by the climate community for sort of policy and by the IPCC for kind of policy decisions and kind of decision making. These are too porous to resolve those straits. So if we look at kind of zoom in, we have a strait here. This is one that we've been testing on. If we look at how this appears in the climate model makes predictions at all these red points, and there are no red points like in the straits. If we were to go to a 25-kilometer grid, which you can see here in gray, we do have some boxes sort of in the strait, and we might be able to get a sense of whether there's sea ice, whether this is open. But in the climate models, we can't resolve these. So it's a difficult problem to answer using climate models. And so the question we are looking at here is, can we use machine learning to enhance the sea ice concentrations to go to downscale to that sort of 25-kilometer resolution, where we might be able to see whether those straits are going to be open or not. And so in this particular task, we want to improve the resolution of the sea ice concentrations that we would get from climate models. So for instance, going from 100-kilometer resolution, which is more of what you would get from a climate model, down to the 25-kilometer scale, which you would need to resolve those straits. And in this particular project, we're downscaling these with a super resolution GAN. And so in this particular case, we're training on ERA5 reanalysis data. So reanalysis data is not climate model data. It's sort of the closest that we have to ground truth for sort of past observations. So it's a combination of model and observation data. And it's sort of a data product, but it's often used in these studies as sort of the ground truth. It's available at 25-kilometer resolution. So in this study, we're just looking at if we were to sort of coarsen the ERA5 data to 100 kilometers, can we downscale with it GAN to see sort of a proof of concept of whether this this downscaling might work with climate model data. And we picked this particular architecture because there's a paper by Harder et al. that include a physics constraint in their downscaling approach. So here we want the volume of ice to be conserved. So we don't want to have like more or less ice depending on the resolution we're looking at. So we want the amount of ice to be conserved between the low and high resolution maps. And in this particular, I don't have the specific results because we're kind of rerunning some of the studies, but the super resolution GAN is outperforming the standard techniques, which in this case are actually just interpolation, so nearest neighbor and bilinear interpolation are what's currently being used. And so we're finding that the GAN does a much better job of downscaling this data. We do have to, look at, right now we're using reanalysis data to train it, sort of to demonstrate the proof of concept. So in the future, we're going to have to look at, how it's going to work with the climate model data. But again, this is kind of an ongoing project. We're in the process of writing up a paper on it. And yeah. Are there any questions about this one? This one's kind of a fun project because it started as a class project of a student who took my class last year. And so it's kind of an unexpected collaboration.
I should comment maybe. This is rather common. You have regional simulations pretty routinely. So you can you can train this again to pretty much arbitrary resolution.
Yeah, I mean, I think the challenge in this case is just, getting the right data. In this case, we're using the reanalysis data. I don't know how many regional models are being run in this particular area, and those models can also be expensive to run. So right now we're just kind of looking at this as a proof of concept and trying to demonstrate that it's, going to be way more promising than just using a nearest neighbor interpolation. I think there's a lot of I have a lot of ideas about different directions we could go in this, but we'll see how it develops.
All right, cool, thank you.
Yeah, and then just quickly, I'll just say with these ideas with emulators and downscaling, we're not just applying them to cryospheric science. So Brown, we're leading this kind of multi-institution project led by my colleague Mano Di Lorenzo about looking at New England coastal resilience, especially coastal resilience to sort of sea level change and increases storms, these types of things that will impact New England. And so for that, I'm part of, with my postdoc and also my colleague Baylor Fox-Kemper, part of the kind of machine learning team. So we're looking at how to downscale climate models to those regional scales, and looking at how to sort of community relevant scales. So looking at kind of specific cities or that we can present information to decision makers. So we're using these same techniques sort of in this project as well, but this is again a project that's kind of just getting up and running. So we don't have a ton of results to show you yet, but it's very similar in terms of the types of projects. So a lot of these applications cut across the geosciences pretty widely. So that's all the material I had to share with everyone. So yeah, thanks for inviting me. And I know we've had some questions, but I'm happy to take additional questions, or if you email me, I can send you, any of the references or answer more questions as well.
Yeah, anything else, Nicole? Well, yeah, I think we're set. Yeah, thank you very much, Karianne. This is fantastic.
Yeah, thank you so much.